The broadcast is now starting. All attendees are in listen-only mode.
Good morning. This is Mark Richardson with our monthly GoToMeeting webinar. Welcome to those of you that are attending this one-hour class. I have Brian Schwartz with me in the recording studio, and we're going to record this session. And today we're going to do some modeling. We're going to look at how we set up a 3D model for animating ODSs and mode shapes or any type of data that we may store into a shape table in ME-Scope. So we're going to look at how we set up rotational components. We're going to use interpolation, and we're going to use some live data off of a rotating machine that we've already acquired, and we'll animate the model and look at it in some detail. Before we do that, one of the other things I wanted to show you was how to import models from SketchUp, which is an internet website where many people from all over the world have stored 3D models of all sorts of things. So we will show you how to do that, because ME-Scope is very useful for animating your data on a more realistic model. Now, as an engineer or an analyst, you may start out with a very simple stick model, just some points and some lines, so that you can look at your data and so that you can verify that you've acquired some good data. But then if you're going to show it to your boss or your client or your customer or anyone else, you may want to import one of these more realistic looking models from a place like SketchUp. Vibrant also offers a service where we will create models for you. We'll charge you a small amount, and we'll set them all up in an ME-Scope project. But let me show you how to use SketchUp. I'm going to go to the Vibrant website, and well, here I'm already in SketchUp. Let's go back to the Vibrant website, and here are the instructions for using SketchUp right on the Vibrant website. So if you go to vibetech.com and click down here and download these instructions, this is a PDF that shows you how to import models from this website. So I'm going to go ahead and do that. So what you do is you go to SketchUp 3D Warehouse, and here's where it's located, 3dwarehouse.sketchup.com, and then you download the model and you import it into ME-Scope. So let's try this out, and you can see down here a blank ME-Scope work area, and then we'll import the model into ME-Scope. So let me go ahead and do that. I'm going to go to the 3D Warehouse here, and there it is. I've clicked on it, and it's brought me into the 3D Warehouse. You can see there's just many different types of 3D models, and there's literally thousands, and it keeps growing all the time. But let's go get something that's perhaps more appropriate for engineering work. I'm going to sort on pumps. Now you can see there's just a lot of different models here. Some of them don't look like pumps to me, but here's one up here that looks like a pump. So I'm going to just hit the download button next to the picture of the pump, and it now put it into my download area on my computer. So I'm going to put this window down and open up ME-Scope and create a new project. This is a standard procedure when we use ME-Scope. We come up with a blank screen here. Now these are previous projects. We'll come back and use this startup page in a moment, but I just want to create a new one, and so here it says create a new project right on the startup page, and I'll say okay, Now it's saved that on the disk for me. Now I'm going to go to the import structure command. So that's under the file menu, and I'll import structure, and here's the Windows file dialog box, and I'm going to navigate to my downloads area, and you can see I've already done this. So here is some copies of the horizontal pump. Here's the one that I just downloaded, so let's just go ahead and click on that one and open it up. So there it is. There's the model, all set to go in Emiscope. And you can see there's some nice detail there. It's even got model and serial number information on it. And this model is simply points, lines, and probably triangular surfaces. How do we know that? Well, I can go up here on one of these buttons. First of all, I can just take the surfaces off. There's all the points. And let's see if there's any lines on this. Oh yes, there's some lines if I take that off. So there's what we would call a stick model. That's just points and lines. And I can also go to the triangle format. Let me make this a little larger so we can see that this is just the outline of all the surfaces. A little hard to see them because of their color, but those are triangular surfaces. So Emiscope will support this, and now I have the light sources on, and you can see what a good job the Windows software and hardware does when I have surfaces like this. Okay, I just wanted to show you that. Now let's go and close this project, and we won't save it. And I'm going to go back to a previous project that I want to work with today. And now it's giving me a message that the acquisition window that's part of this project is not, the hardware is not available. That's okay. I'm just going to click through, and now let's just look at what else is in this project. So I'm up here on the project panel. I've got a model. I've got some data blocks with data in them. You can see some spectra there. And then down here I've got a shape table of the first order of this rotating machine. So let me open that, and I'll rearrange my windows so that we can see everything. Okay, so I have a shape table that I've already obtained by saving the peak values at the first order, and you can see that I've got 24 degrees of freedom, or 24 measurements in this shape table, and we can animate this data on the model. The model's already been set up. We're going to go back and kind of pick it apart to see how we would animate this data on this particular model. Before I do that, let's go look at some pictures of the actual machine that we took this data from. So here it is. This is a rotor kit. It's got a variable speed knob here and an on-off switch. This is a little power supply. It's got a couple of rotors, and you can see that there are some accelerometers. These are triaxial accelerometers. There's one on each of the bearing blocks. There's 6 of them on the base plate. So a total of 12 accelerometers. Over here you can see the tachometer that's going to measure the rotating speed of this machine. So here's another view of it. You can see the tachometer a little bit better. This tachometer is a BNC-based tachometer, so we treat that signal just like a vibration signal coming from an accelerometer. So this goes into the analyzer along with the BNC connections from the 8 accelerometers. So total of 24 degrees of freedom in our shape table from the accelerometers, plus we use the tach signal to locate the first order or the running speed of the machine. Here's another view of it from the back. You can see the wiring coming off of the various accelerometers here, and then here's the motor and a rubber belt that drives the shaft here with a couple of rotors on it. So this little rotor kit is good for demonstrating on balance and various other machine faults in rotating equipment. Let's go over here and start the animation. And so I'm going to come down here. I right-click in the structure window and just say Animate Shapes. So here is an animating model of that rotor kit, and you can see that on this outside rotor is a piece of reflective tape. You can see that tape rotating around. That's what's triggering the tachometer. So we're getting a once per rev signal off of the outboard rotor here when the laser reflects off of the reflecting tape. And the reason we put that on the model here is so that you can see in ME scope the speed of the ODS, in this case 1440 RPM. Let me make this a little larger so you can see that. The animation, of course, is slowed down, but the main rotor has been made to rotate at exactly the same speed, 1440 RPM. Where did we do that? Let me just show you that real quickly, and we're going to come back and review some of this. But here are all the parts of this machine. We call them substructures. And if I go down in here, again, I'm going to click in this spreadsheet, hold down the control key, and spin the mouse wheel so I can see things a little better. Okay, here you can see that three of these parts, the shaft, the inboard rotor, the outboard rotor, and then down here the shaft pulley, that's this pulley here in the back with the rubber connection to the motor, the rubber belt. They're all rotating at 1440. The motor pulley is actually about 3 times faster, and that's because the motor has got a smaller diameter than the motor pulley. And you can see we've indicated a different color there, so you can see that rotating also. So these are substructures that have been defined on this model, and then they've been in the substructure spreadsheet. We say that these are rotating. Now, where do we do that? Well, let me drag this over. Rotation, I'm going to drag this column all the way over here, and we'll park it right next to the speed. So I can drag and drop any of the columns in the spreadsheet. That's true of any of my spreadsheets. And you can see now that we've got 5 different rotating substructures on this model. Okay, well let's start out and just start and see how we would set the animation up on a model like this. We're going to start with the shaft that the rotors are mounted on, and the data, of course, is coming from the 8 accelerometers. Let me just stop this and we'll I'm going to draw I'm just dragging and dropping the point labels of those points up in the air a little bit so we can see them very plainly. And so there they are, and then there's one more over here in the back. So there's my 8 test points, and I'm getting 3D data, XYZ data from each of those 8 test points. Now let me just hide everything, and we'll focus our attention just on the shaft, because we want the shaft and the rotors that are on the shaft to follow the motion of the two accelerometers on the bearing blocks. So that's where we're going to start out, and then we'll work our way down to the bottom, and we'll use the accelerometers on the base plate to animate the bottom, the base plate, the bottom of, well, we'll get the power and the motor and so forth to animate from the base plate once we set that up. And then we'll do something a little different with the bearing blocks, and I'll show you how we interpolate between the bottom of the bearing block that's attached to the base plate and the top, which is being driven by the accelerometer mounted on the top of the bearing block. So the first thing I want to do is hide all these. So I'm hiding them all. Now you can see we've got the axes here. Let me remove that also. I'm going to go to Options, and under Labels, Axis Lines, I'll turn that off so that's not going to distract our attention. So now we have everything hidden. I want to go back and turn on the triaxials. So there's all of the data that's, or the points that are actually where we took data. And we'll also turn on the shaft up here at the top. So there is the shaft, and if I start the animation, you'll see that there's the points moving around, but you can see that shaft is simply following the two accelerometers. Now, as we take different data at different running speeds or under different operating conditions of a true rotating machine, these two accelerometers are going to behave differently. Now, this is just being animated with a single ODS here at 1440. As we change the speed of the machine, the ODS changes. And so we want this shaft to pay attention to the motion of the two accelerometers on the mounted on the bearing blocks. All right, well, let's just start all over and stop this. And the first thing I would do then is assign my measurements to the accelerometer. So I'm going to select the accelerometers. Now, they already have animation equations associated with them, but let's go clear those out. And so I'm going to go in here and we'll just set them up again. So I'm going to go under Draw, Animation Equations, Delete the Equations. So this is going to delete out all the animation equations for those. Now it says you have points selected. That's fine. Do I want to unselect? No. And this is just going to clear the equations. So it cleared out 24 equations. That's what I'd expect because there's one equation animating in each direction at the 8 points. So now I'll just go back and recreate those, and then we'll look at them. So I'm going to go back here, and now I want to create measured equations. Remember, the measured equations are going to use the measurements in the animation source. And there's two ways to do it. We can do it manually, or we can do it by matching up the points and directions on the model with points and directions in the animation source. So we're going to do this one because our animation source is our first order ODS data that we looked at previously, the 24 measurements. So let's go ahead and do that. Again, it says you've got things selected. Remember, in Emiscope, if I select things, then I focus my attention on the selected. I'm going to go ahead and say no. And now it's saying animation equations at selected points will be deleted. Well, we already deleted them, so. Okay, it only created 18 and left out 6. Why? It didn't get 1 through 6. Let me go look at my data and see why that might have happened. Not a reason why, for sure.
Are points 1 and 2 labeled or on?
They aren't. Points 1 and 2 are not selected. So somehow or another, points 1 and 2 did not get selected. So now what I can do is I'll go to the points. And there it is. You can see the red ones are selected, the blue ones are not. Now, they should have been selected as part of my substructure. Let's go back and see why they weren't selected. I'm going to toggle this. Okay, now they're selected. So somehow or another they got unselected. Now you can see they're all selected. So let's go back and do this again. Animation equations, create measured, and we'll say yes, and we'll say no. It's unselecting them right there. So there's the problem. Let me go and select them manually and try this again. Create animation equations. No. Yes. Okay, we got 24 this time. So now if we go and look at those animation equations, let's go look very quickly at, so down here I'm going to say show the equations, and I want to see the measured equations. And there they are. So now you can see that point 1 is being animated with measurements 1, 2, and 3. Point 2 with 4, 5, and 6. And so the measurements over here, the way they're numbered is very important for the animation. We need to set those up, or once we've established a set of measurement numbers over here, those will be used by the structure window to animate each of those points in each of those directions. Okay, so let's go and look at how we got not only the shaft to animate, but to rotate. So there's two issues here. Let me turn the display off. I'm going to go back here and say nothing. I don't want to see anything. And now let's just look at this shaft. I'm going to go back to Substructures, and let me hide the test points. Now let's just look at the shaft. If I hide the surfaces, you can see better what the shaft has in terms of points, and you can see that there are a number of center points. Now a center point is defined in this point spreadsheet. If I go to the points, the center point is defined by other points referencing it. So if I go through my point spreadsheet here and look for, first of all, we've got the test points, the 8 accelerometer test points, but they're not visible. You can see they're invisible. If I scroll down here to look for some of the visible points, I'm going to go way down here into the spreadsheet because there's a lot of points on this model. Okay, so here are some of the points, and you can see that this column here, this is a center point. So some of these points are referencing a center point. And the different center points are are 27, 28, and 27. And so if I click on one of these points here just to see where it is, well, I don't see it, but it's one of the points on this shaft. And if I animate, now here's the other thing we can do. Let's not animate with the shape data. Let's just animate with no source. And if I turn on the animation, you can see that each of the radial points is rotating around a center point. So those had to be defined by selecting the points one at a time. We went along each of the axes and selected a group of points, and then we assigned them to a center point. Now the center point is going to animate based on the data from the two bearing block accelerometers, and then the radial points, what we call radial points, rotating around each center point, are going to animate based on the motion of their center point. And we'll use interpolation to do that. So let me just show you very quickly how we would set that kind of thing up. First of all, we go and put the, I just want to select the center point. So let me stop this. And I'm on point. So if I go through here and expand my display, and I go and just select, you can see that point there lit up a little bit. This one is lit up. I'm going to select each of these center points.
You missed the first one, I think.
Yeah, that's because there's a couple of them there.
Okay.
I think I have them all. Now what I want to do is go back and make my accelerometers visible, and I'm going to select, oh, can't do that. I made them visible. Now I have to go back to points, and I want to select my two test points. So if I scroll through here just to check, I should have my two test points. Those are 1 and 2 in the spreadsheet. You make this a little larger so you can see. And then down here I should have all of my there's a center point there at 1813, and then there's a bunch down here at the bottom. So I've got 1, 2, 3, 4, 5, 6. I should have 8. I don't see them all.
We had the one selected earlier.
Okay, well, you get the idea. What we're doing here is getting the if I put the source back and I start the animation, all those center points are following the two accelerometers, and then each set of radial points is following its own center point. And that's the way the model is built up. If I put one of the wheels back on now, let's go to one of the let's go to the outboard rotor. Same thing here. Now this rotor, the center point of this rotor is first of all animating based on two of the surrounding center points on the shaft. Now, in order to do that, we not only need to select them, but we need to convert them to measured points. So once their animation equation is set up, we go and use this command here, interpolate it to measured. And that turns those interpolated points into measured points. And then the same idea, each of the radial points on the rotor is made to follow the motion of its center point. Well, we're not rotating here. Let me see what happened. Stop. We'll unselect. Okay, so there we go. So that part there is just rotating about its center point. You can see its center point right down there in the middle. And that center point is following the two center points on the shaft. So that's how we get that rotor to rotate. And then all the other ones, let's just bring them back in the picture. And down here we have the shaft pulley. So all of those were done exactly the same way. You can see they each have a center point, and their center point, in the case of the pulley down here, is following the motion of the two nearest shaft center points. And then, of course, we set them up as rotating components. Now, the motor pulley is a little bit different, but the same thing. We've got the motor pulley rotating. Let's see, motor. Let's put the motor in, and here's the motor shaft. Now, we didn't make the motor shaft rotate, but it's following the motor, and the pulley is following. You can see it's got a center point there too, that green one, and it's following the motion of the motor. So you have to build it up a step at a time, and then as each point is interpolated, convert that to measured, its equations to measured, and they will stay fixed as you interpolate other parts of the structure. All right, let's go down and look at the base and see how we set that up. That's a little bit easier because I'm going to hide everything again. It's simply a flat plate. So let's turn on the base. There it is, and then we'll turn on the accelerometers again. Now here we only want to use the accelerometers that are actually sitting on the base. You can see something else interesting here. This accelerometer is a different type where it measures X and Y at 45-degree angles to how the wire comes out of the accelerometer. If we go back to the picture, we can see that. So there it is. You can see this accelerometer is a different type. So in ME-scope, we can orient each accelerometer because each point has its own local axes, and we can orient the local axes of the accelerometer exactly like they are oriented on the test article. So we don't need to worry about pointing them all in certain directions. Okay, so how are we going to do this? Well, let's select all the points. Let me do this a little differently. I'm going to go over to points as my current object. Let's unselect everything. And first of all, I'm going to just select half of the points and 4 of the accelerometers. So I would do it this way. Draw a selection box around all of those points. Before I do that, let's make sure we got the equations cleared for the base plate, because see, it's already animating. Let's just start the animation. So you can see that the base plate is following those accelerometers around. But let's go back and stop that and unselect everything. And I'm going to select those points again using the selection box. But now I'm going to unselect. You can see here in the spreadsheet points 3, 4, and 6, and 7 are selected. I'm going to unselect them. And now I want to delete the equations for the base plate points. So delete their equations, and no, yes. Okay, so there was 120 equations there. Let's go back and recreate those. So I'm going to go back and select those points again, just those 4, and I want that part of the structure to animate based on those 4. So I'll go in here and I'll say create interpolated. And again, I don't want to unselect. And I'm going to use all 4 of them. So it says number of nearest measured and fixed degrees of freedom. And we're going to go ahead and say there's 120. So if I animate this, I can see that I got pretty good motion there. Now I may want to just change things a little bit. For instance, these corner points here, I could just have those follow the accelerometer that's right close to them. So how would I do that? Stop the animation, and again I'm going to draw a selection box, but this time I'm just going to include the accelerometer point and the 2 points below it. And I could go over here, and if I hold down the shift key, I could do the same thing and add to the selection the other corner point. So now I want those points to simply follow the accelerometer's motion right above it. So I'll go create interpolated. No, I don't want to unselect. But this time I'm going to say follow the nearest point. Okay, it recreated 12 equations. So now if I look at the animation, you can see that those corners are following exactly. Now here in the middle, I've got a problem because I don't actually have some points right there. So I've got to perhaps do the same thing, but use the points on either side and animate them with the accelerometer in the middle. So let's just do that. So here I'm going to turn this up so I can use the selection box again. And I'm going to select just those. And then I'll do it again over here on the other side. Hold down the shift key and select those. And now I'm going to say on either side, animate those points with the nearest neighbor. So I'll go to interpolation, create interpolated, no, and just 1. So let's see what that looks like. Okay, so there we have the plate following. Gee, is that a good interpolation? Well, maybe yes, maybe not. You can see how the interpolation, even with rigid body motion like this, I may want to just go back and have those center ones move around independently. Well, let's just do the other half of the model. So we'll do the other half of the model. I'm going to stop this, and I want to select first of all the base. So I'm going to grab all of these points like this, and I'm going to unselect 4, 5, 7, and 8 and clear out those equations. And now we'll go back and select those points, and we'll interpolate want to use 4 nearest neighbors. So I recreated them. All right, now what about mounting the parts on top of the base plate? Because we got the base plate moving now following those accelerometers. And now let's go back to the we have a lot of different points here, so, or a lot of different substructures, I should say. I have a power light, a power switch, a fuse, a speed control, and what else?
Motor control.
Motor control, there it is. So all of those, we would like that to follow the points on the base plate. Now that we have the base plate animating, we would like all these points to pretty much follow the points perhaps on the base plate that are closest by. So let's just start the animation and see what it's doing here. And we can see that, you know, because this point over here is so active in the corner that there's a lot of points there on all those pieces of the power, or the power supply, or the motor control. So we may want to just take the base plate, the interpolated points, and so let's go do that. We've got the base plate animating now, so we don't need the accelerometers anymore. So we can hide them, and we can work just with the base plate itself because it's already got some motion. So let me go stop the animation, and I'm going to select, let me just do it by selecting the points on all these different substructures. So I'll do that by selecting the substructures themselves. So I'm going to go in and let me unselect the base plate, and there's some points. Okay, so we got them all selected now, and I'm going to delete their equations. Okay, so that was a bunch of equations. If I start the animation, we'll see that it doesn't move. Now here it's saying that you have points that do you want to that don't have equations. Do you want to create measured equations? I'm going to say no, and so no measured equations were created, and animation didn't start either. So let's go ahead and now take the points on the base plate. I'm going to select the base plate. Let me unselect everything. We'll select the base plate, and we'll convert all of its equations to measured. So interpolated to measured. So they will not be involved in the interpolation. So we're going to use those as measured points. Everything should animate just fine. But we deleted the equations on the rest of it. So now let's go and see if we can make the rest of it animate in a realistic manner. I'm going to rotate it up here, and I'm going to go to points. Remember, the animation equations only involve the points. So I want to rotate this thing around, and I'm going to draw a selection box to grab all the points. Now I could do it with substructures, or I can do it with the points themselves. So there it is. I've grabbed the ones on the base and all the ones that I need to interpolate now. And let's just go do the blind one. We'll do the create interpolation, and we'll do for the 4 nearest neighbors and see how that animates. You can see we created over 4,000 equations there. And so there it is. There's the animation. If I go back and make everybody visible, we'll go back and look at the, okay, see, we had things selected, so I can't, I've got to unselect first, and then I can make them all visible, and we get our model back, although it's, because of the selection, it won't animate. So let's now start the animation and the rotation. And I'm going to center it up here. Turn the surfaces back on. You can see it's very useful to turn off surfaces. I can turn off the points. And there's the model. And let's look at one more thing, and that's how to do the interpolation on a bearing block. So we didn't look at that. We've looked at the base plate. We've looked at the motor control and the rotors. Let's look at the bearing block, because you can see here we've got an issue. We want the shaft to follow the accelerometer that's on top of each bearing block. However, we want the bottom of the bearing block to follow the accelerometers at the base plate. So you can see it's a little bit unrealistic here, but the way I set that up was to do some interpolation, first of all using all 3 accelerometers, and then go back and make the center of the shaft, the bearing itself, and the cutout follow the top accelerometer. So let's go ahead and do that. We're going to go back to Substructures. Let's hide everything. And I want to pick out outboard bearing housing. There it is. We'll get the accelerometers. And we also need the outboard bearing. So there's the parts that we need to animate. And again, I'm going to turn off the surfaces because it's a little easier to see the points. Again, we're working with points here. And you can see a lot of parts there, but none of these are rotating. Let's start the animation. Again, we can see what they look like right now. And so how did we get them to animate like that? You can see all of the bearing housing and so forth are just following the accelerometer on the top, and then the base plate is following the ones on the bottom. So I'm just going to go in here. I'll go back to points. And first thing we want to do is draw a selection box and select the points that we're interested in. Now we don't want to delete the equations for the 3 test points. So those are 0.6 and 3 and 1. But let's delete the other equations so we can start over here. we'll delete those equations. All right, there was 500 equations there just for that little part. Now what we'll do is turn them back on again. 1 and 3 and 6. Those are my test points, or they already have measured equations. We looked at those earlier. And let's create some interpolated equations for the rest of it. And here we could say 4, we could say 3. There's only 3 there, so if we say 4, there's the equations that we created. So if I animate, you can see that everything's moving around. However, the center, which is going to house the shaft, is not following the accelerometer on the top of the bearing block. So I'll go in there and just grab the top portion of the bearing block and make that follow the accelerometer sitting on top of it. So I'm going to go back and stop this, and let's just go in and select. Again, I'm rotating things around so I can select just the part I'm interested in using the selection box. I'm going to select all of those parts. Now I don't care about these ones on the outside here, so I can unselect them, and I'll do that by holding down the control key, and you can see as I move the mouse around, it enlarges the closest point. So I'm going to unselect those 2 points, and then we'll go to the other side and we'll unselect those also. And so these now I want to create new interpolated equations just to follow the motion of the accelerometer. And this time we're only going to use the single accelerometer, which is all that's really there. Now if I start the animation, you can see that things are following a little bit better. Let's stop it all and go back to our substructures, and we'll make them all visible again, and we'll start the animation, and we'll put the surfaces back on, and we'll turn the points off. So that's how we did the interpolation on that bearing block. And then a similar way to do the inboard bearing block, did the same thing there. A few more little tricks, but I think you've seen how all the interpolation is set up. The belt is not actually moving, it's just riding on the 2 pulleys. So it had to be set up so that its points would follow the motion of the nearest radial points on each pulley, pretty much doing exactly the same things that we've already done with some of the other points on the model. So that pretty much wraps up what we wanted to show today. Brian, do we have any questions from the audience?
We had one earlier saying it looked like it was already animated. How is this different? I think just, talking about, how to tell if you've got a good set of interpolation equations, maybe.
Okay, the question was, how do you know whether you have good interpolation equations? We looked at a few of the measured equations that were very simple. We haven't looked at some of these other interpolation equations that involve numerous points. For instance, on the base plate, we use 4 test points to interpolate the motion of the base plate. And it's simply a geometric interpolation. So it's the answer to the question, how do you know whether they're correct, is more a question of, does it look good? Does it look like a realistic animation? And again, it's based on the distance of a test point from an interpolated point or an unmeasured point, and you can only take it so far. We have a new tech paper out, and maybe next month we'll show how we can actually take a set of mode shapes and expand some ODS data, like this data that we have here, where we've got 24 degrees of freedom in this shape table that we're actually animating the model with. The model has got literally thousands of points on it, and I showed you how to set up the interpolation, but a more accurate way to expand a set of data where we've only got 24 measurements is to use a modal model. And so we'll show you how we actually built a modal model of the base plate and the bearing blocks. Very easy to do in Emiscope. Used SDM to attach the bearing blocks to the base plate, and then use those mode shapes in a curve fitting scheme, a least squared error curve fit, to fit the ODS data, and we can do that in real time. So as the ODS changes for the 24 accelerometers, we can change the animated picture for literally thousands of degrees of freedom. But the base capability in Emiscope is to use the geometric interpolation, and it comes up with a pretty realistic picture. Certainly all these rotating points on the shafts are being animated from essentially 2 accelerometers. X, Y, Z. You can see some motion here along the direction of the shaft, along the, let's say, the Z-axis of the shaft, and so we're getting true 3D motion, but interpolation is only going to take you so far. All right, we're going to wrap it up here. That was the only question we had today, and we'll see you next month, and we'll explore some more. Maybe we'll go into the shape expansion and the live data acquisition. I should show you how we actually take data on this machine, and we can vary the speed and pick off the peaks from any of the orders, but in this case it was the running speed at 1440 RPM, and then animate that data essentially in real time. So we can get a real-time ODS off a machine like this, where we have a tachometer signal telling us what the speed of the machine is. All right, we'll see you next month for those that want to learn more. Have a good day.